I'm to talk about closing the blockchain with this title, Toward Achieving Unanimity for Implicit Closing in a Trust System. Speaker is Michiyoshi Imamura. Here is the outline of my talk. First, blockchain is the underlayer technology of a decentralized system that allows an unspecified number of users to participate. It has a feature that the availability of the system depends on the users. Popular projects that use blockchain technology guarantee continuous availability. Then, do all blockchain-based systems have robust availability? We intuitively know the answer is no. We assume that it is closed, but the process is not clear. This study focused on the process of the nearly closed project in order to clear the mechanism of closure. In short, this research question is: can we systematically explain the closure of distributed systems based on the blockchain technology? We worked on 3 tasks to establish a closure method for trustless distributed system. First, build a framework as a base for discussion of closure. The next step is to empirically check the correctness of the framework based on the observation result. Finally, we discussed the implementation of an explicit closure function. Okay, in the next slide, we propose the framework. First, a distributed system based on blockchain technology does not have the function to close. Hence, we need to define the closure of the system. In this study, we used a model based on the 3 laws presented in previous study to systematically discuss the closure. The 3 laws are categorized as sender, miner, and recorder. This model is represented by a cyclical structure in which the continuation of the system is established by the function of each law. We derive rules from user behavior in each law. Here is a description of the function of each law. The sender obtains the block required from signature from the recorder, creates a new transaction, and sends this to the miner. The miner collects the new transaction to store in block, and locates a hash of that block to store the transaction. When the miner finds the hash, it broadcasts the block back to the recorder. The recorder accepts the block only if all transactions therein are valid and not already spent. It then mirrors the latest block status to other nodes on the network. The recorder's mirroring path duplicates the ledger and creates propagation path that is used in transaction passing by sender and miner on the blockchain network. This cyclical structure works to keep the network update and the service going. In other words, closure means that the law ceases to function. It ends when everything ceases to function. The framework proposed in this research uses the event that occur in the cycle when each law ceases to function as rule for closure. Stopping the function of the cyclical structure is implicit consent to closure. Next, let's look at what happens to the network when each node stops working. First, we consider the sender. Because the sender's role is to propose transaction, give up the role means that transaction proposal will cease. When the sender stops proposing, the number of the transactions stored by the miner in the block gradually reduces. The cost of storing an empty block is lower than that of storing a full block, because the recorder always keeps an empty block. Next, we consider the miners. If we lost the miners, no matter how many transactions the senders broadcast, they will not be verified. The role of the miner is to validate the broadcast transaction in the blockchain and to record them in a new block. If the miner gives up their block, it means that new block will cease to be created. New block will never be sent to the network. The recorder is not able to change the new blocks, and the block header stops updating. As a result of the loss of the miner, there is a time lag in the interval between blocks, and the blocks stop being updated. Finally, we consider the recorders. When recorders give up, the sender can no longer determine the network status. The miner cannot catch new transactions and continue to generate empty blocks through self-mining. To lose the recorder load means that data cannot be recorded and they are just destroyed. When only the recorder agrees to closing the blockchain, it represents a final consent, unlike those of the sender and miner. The next step is to acquire empirical knowledge by observing the actual network. Our analysis covers 290 minor cryptocurrencies listed in crypto ID, including those listed in the middle of the observation period. The main status are shown on this slide. First, we followed the framework and focused on the number of transactions and new blocks contained in a block to examine the behavior of the sender and the miner. The period of zero transactions and zero blocks in a day are shown in this figure. The white area indicates a period where more than one transaction or block was identified in a day, and the black line indicates a period of zero transactions or blocks in a day. 124 currencies did not have a single transaction in a single day during the observation period. There were also 46 cryptocurrencies for which at least one new block was not created during the day. Next, we investigate the projects that were announced to be closed by the community during the observation period. We don't know if we were lucky or not. We came across a stopped project. The following figure shows the intraday transaction and blocks fulfillment rate for the stopped project. The gray area in the figure shows the case where the empty block rate was less than 100% during the daytime. The blue area shows 100% and the red area shows the period when no new block was created. And we find two interesting points that confirm the effectiveness of the framework. One is that the creation of a new block stops after an empty block. The other thing is that it is difficult to reach unanimity on a minor cryptocurrency that is as close to closure as possible. In addition, a carefully look at the dynamism of blocks show more information about their condition. This figure is empirically classified into three levels based on change in the level of mining difficulty and interval. These results provide us with a useful empirical rule for isolating the early state. We can assume that follow a model in which mining difficulty is stable and mean regressive. A non-sequential change in mining difficulty that exponentially decreasing can be an indication of minor dropout. And we confirmed that in the last stage just before the mining stopped, the block interval was longer and the block delivery speed was less stable. Finally, we investigate the relationship between closed project and node distribution. This figure represents the distribution of the average number of nodes for the 80 cryptocurrencies that experienced an empty block or a new block suspended during the most recent period. Uh, 83 currencies were broken down into 6 empty blocks and 20 new blocks that were suspended. The important things that we can say from these results is that it is very hard for any unpopular project to lose all nodes. Applying the result of the empirical analysis to the framework, what can we say? From the framework and the empirical analysis, we find that the number of transactions and blocks was significant for the closing unanimity. Focused on the agreement of no new blocks, we find this state is equivalent to the first time the blockchain is launched. In other words, we can create the same situation as closing through initialization, which overrides the data previously stored in the ledger and erase the historical data. We consider an implementation based on this knowledge. The implementation presented here changes the starting position of the block when the number of empty blocks is consecutive up to a set threshold. We use two parameters for this implementation. One is a group of dummy blocks to switch this generation position. The other is a continuous distance L of empty blocks. The record receives an empty block from the miner as the starting point for the switch. After building the block, if all L blocks are zero transaction blocks at the creation of the nth block, the genesis block is changed to the nth block and the blocks before n minus L range are deleted. The initialization of the ledger propagates to all existing records in the network by the nth block. When a new record is connected to the network, the existing record mirrors the initialized ledger, so that the discarded blocks are never restored. In this research, to deepen the discussion on finding the unanimity required to close blockchains, we propose a framework for mechanism analysis that focuses on the 3 user roles in blockchain. We consider the user behavior that did not contribute to the cycle of roles as voting without interest, and visualize the impact of the flow, the block and block transaction in the system. Then we confirmed the validity of the proposed framework on the minor cryptocurrency using blockchain that we assume to near closing. Finally, based on the framework and the empirical analysis, we discussed method of implementing a mechanism for closing the blockchain. Thank you very much for your listening.